So today we will cover the lecture 5 transformation. So first of all, what is a 2D transformation? 2D transformation means a change in either position or orientation or size or shape of a graphics object. The object can be a line, circle, arc, ellipse, rectangle, polygon, etc. So you see, if you change the position, orientation, size or shape of a graphics object in a computer graphics, that means using the help of computer programming, that can we call a 2D transformation. This line, circle, arc, ellipse, these are some basic shapes and objects that we will initially use to learn how the transformation work, so that we can actually apply transformation in a complicated objects like character and other objects whenever that you see in a game or in a movie or in other places. So that's where we will start and gradually we will evolve. Now let's go back to the slide number 1. So as you can see, transformations are fundamental part of computer graphics. We basically use transformation everywhere. Okay, in order to manipulate object in two-dimensional space. So we know what is a two-dimensional space. So the screen that you are seeing is a two-dimensional space. So what have a length and the width is a two-dimensional space. So in order to manipulate object in two-dimensional space, that is your computer screen, we must apply various transformation function, and that allow us to change the position, size, orientation of the object. So let's assume you're watching a video of you're playing a game where you can actually kick a football. Okay, so whenever you're kicking a football, that is also actually a 2D representation. Okay, now there are two types of transformation. We have a geometric transformation and we have the coordinate transformation. In the geometric transformation, the first object itself is moved related to the stationary coordinate system or the background. The mathematical statement of this viewpoint is described by geometric transformation. So basically, we have an object and we have a background. So what we will do in geometric transformation, we will see how we can move the object in different places. We can change the size, we can change the position, we can actually zoom it, we can zoom out. That means we can scale it and scale down. And in coordinate transformation, we'll work with the background. So this is a basic idea about the geometric transformation. The object is in the plane, is represented by a set of points, that is vertices. The object and the plane can be described as a set of points. So any object that you see in the screen can be say that this is a collection of set of points. So for example, the screen that you are currently seeing, okay, if I say that this is also a 2D plane where each of the lines that you are reading is actually a collection of objects, or sorry, collection of points. Every point P has a coordinate xy, so the object is the sum of total all its coordinate points. So what does this mean? This means that let's assume that in a lecture 2, whether you have learned how CRT monitor work or how LED monitor work, if you remember, in CRT monitor we used an electric gun to draw pixels or the pictures in the computer screen using a phosphor. So whenever we are drawing a picture in the computer screen, we exactly need the point where there will be 1 and where there will be 0. So we use a frame buffer where each pixel has a value 1 or 0. In a black and white image, it's 1, 0. In grayscale image, it's 8-bit. In a color image, it is 24-bit. So everything that you see in your computer screen is actually a collection of points. So each point actually has a coordinate. So basically, you see here you can see a point. So this point, let me underline. So you see the point that you see here and this point, those have different coordinates. So if I assume that this is the x and y axis coordination, so we can say that all these points that you see here, all the S, the O, the comma, all of them are actually collection of different points where each point actually have different vertices or different coordinates. Now, so this is the basic idea about the geometric transformation. So basically everything can be represented as a set of points and each point will have a x and y value. And it is also related to the resolution. If you remember, the more resolution you have, okay, the more points you will have in the screen. If you forgot about how resolution work, you can actually go back and see previous lectures. In that lecture, in short, in one screen, if the more points or the more pixels you have, okay, that means the better the image quality will be. So we have already seen the definition of 2D transformation. We have seen that these are the types of basic transformation that we can apply. We have a translation, we have a scaling. Translation means moving object from one place to another place. Scaling means making it, changing its size, making it bigger, smaller. Okay. Rotation means actually changing the angle. So rotate 90 degree, rotate 180 degree, 70 degree. So basically if an object is like this, object is in like this, if I rotate it by 90 degree, okay, the object will become like this. If I rotate it by 45 degree, the object will become like this. So this is a simple example for a line, but if there is instead of line, there are other complex objects, we have to calculate that as well. So we will see how we can actually do the calculation. And then we have the mirror reflection, that if we stand in front of a mirror, we can see actually our reflection. So in a computer graphics, how we can actually represent the reflection. So this is actually a very interesting concept. And then finally we have the shear. So we'll actually talk about them one by one. And now let's start with the translation. So in the last class, I have talked about translation in details, but I will give you a brief idea one more time. What is translation? In translation, an object is displaced a given distance and direction from its original point. So basically, if you have an object, if this is your screen, let's assume this is the computer screen you have. Okay, so this is your computer screen that you see the border, and you want to move our object, that is this house, from this point to this point. So for that, we actually need translation. So first we have seen how translation work for a single point, and then we have seen how translation work for a line, and then we have seen how translation work for a triangle. So same way, if we actually can find out the outlines, we can actually translate any object from one point to another point. So let's go back to the example that we have seen. So let's assume that we have, this is our x-axis, this is our, this is our y-axis, and this is our x-axis. So initially there is a point in the graph was in this point. The point was, let's assume this is 2, 2. And then there was a point in this place, okay? So let's assume the point, this point is named P. Sorry about the handwriting. This point is P and this point is P prime. Okay, so let's assume this is actually 7 and this is actually 7, 7, okay? So translation means the process in way you can actually transfer this point P to the P prime. So you can translate this point P to P prime. So there are two types of questions we get in this from this translation. First one, that you will be asked that if I want to move a point from this place to this place, what changes I need to make? Now I'm sure all of you can guess that this point is 2, 2 and this point is 7, 7. So that means if I want to move this point to this point, I have to add 5 in the x-axis. I have to add 5 in the y-axis. So this actually doesn't look equal, but let's assume both of them are equal. So I have to add 5 in x-axis, I have to add 5 in y-axis. And in this way, I can actually translate the point from one place to another. And that's where actually this one comes in. So you see the figure that we've seen in the last class, that here, the point 2, 2 can be actually translated to another point, that is the red one, by adding some values in x-axis and y-axis. So the bookish definition for this is that a translation moves all points in an object along the same straight line. So every point will be moved from one place to another place. Now we will come back to this later whenever we are talking about the triangle. But first, the path is represented by a vector. It is called translation. So basically, you see the green line here that you can see, this is called translation or the shift vector, because initially the point was here, then now the point is here. We can write P prime X. P prime is the new location of this. So we can say this is the P prime. And this is the P. So the P prime, the new location will be PX. That means the old location or the old coordinate plus TX. That means this one. So this is basically a inter-level geometry. I'm sure that most of you already know this, but I'm just, in case you don't know, that's why I'm covering this. And then same way, PY prime, the new location will be PY plus TY. So PY, that is this two, and TY is this one. Okay, now, if I can write in this way, okay, or I can write in this way. You see, P prime equals to P plus T. So this is actually called a matrix form. And what is the advantage of writing like this? You see here I have to specifically mention px, tx, py, ty. But if I write in a matrix form, okay, it will automatically do the calculation for x and y. This is number one. Number two, you see the x prime y prime here equals to xy, there's a bracket plus tx ty. So that means I can represent in this way or I can represent in this way. Now why I will want to represent in this way? Because I might find this one is very simple, just adding some values, because this is a simple addition. After we are covering the scaling and after some other topics, we have to multiply, we have to divide, and so on. And if you actually use a matrix, those operations actually becomes much easier. So that's why whenever we're using translation, it's better to use the matrix. Now let's go back to the previous slide. So we know how to actually translate one point from one place to another place, but I don't want to translate a point. I want to translate not a point. I want to translate, let's assume, a line. Okay, so let's assume this is the line. The line has 2 points. Okay, let me line the coordinates. The line has 2 points. 2, this is 2, 2. Let's assume this is P. And this is, let's assume this is Q. And the value of this line is basically 3. Also, not this should not be 3. Let's assume 8, 6. So value of this point is 8, 6. Now, if I want to translate this line, that means I want to move this line to the new location here. Or I want to move this line. Let me change the color. Okay. I want to move this line to this location. So how can it be done? Or I want to translate the line to this position. How it can be done? Okay. So this is the questions we will answer in this chapter. So let's first start with the simple one. Okay, I want to translate this line to this line. So what I can do, I can first see that what is the coordination of this point or this point. Okay, so let's assume this is actually 1, sorry. Let's assume this point, that is P prime. Okay, so P prime, okay, I don't have prime here, so let's name it L. I want to translate this P point to this L point, so that this is my shift vector. You see this straight line between these two, this will be my shift vectors. What is a shift vector? We have just seen the definition that the path represented by a vector called translation or shift vector. The path between 2 points. So basically the path between this P point and the L point. Now again the question resumes, how I can actually transform from P point to this L point. So what I have to do, I can see that this is x-axis, this is 2, and this is y-axis, this is 6. So that means in the x-axis, the value increased by 6. So we can write x equals to 6. So if you write x equals to 6, and let's go look for the y. You see y is 2 and y is 1 here. So basically y decreased by 1. So we can write y equals to -1. Instead of writing xy, we can write tx and ty. So basically, whenever tx and we translate by tx, that is 6, we'll get this point. If we translate by ty, that is -1, we'll get this point. So you can actually see, or you can calculate that if I want to draw a line from here to here, how much distance I have to move one single point. And all the graphics work that you see, we actually work with some basic, very basic translations. Now let me erase this tx and 2y, they're looking very ugly. But you get the idea. Now let's go back to our slide. So this is all about the first slide, and now, sorry, the second slide. Now in the first slide, we now actually want to represent a complex object. Okay, we are not instances simple objects. So whenever we are working with complex object, what we can do, let's assume I will change this one. Okay, and instead of taking straight line, I will take a triangle. So because a triangle is lot similar to the house, so let's assume, let me take a triangle of this is my first house. Okay, and this is my house where I live. This is where I don't live anymore. Okay, now So this triangle, what it will do, it will first, what I have to do, okay, let's assume this is the house, okay, and we want to translate this house from this place to this place and assume these two are equal, okay. I know there is no house like this, but for now let's assume this is the house and they're equal. Let me try to draw them as equal. Let's see whether it's possible. Yeah, now they look a little bit equal. So I want to translate this house from this point to this point. So the first thing that I have to do, I have to actually find out the outliers or the boundary points. We'll discuss about more about them later, but let's just now select any 3 points that will actually help us to translate this diagram from this point to this point. So let's assume I'll take A, B, C, and the location of A is, let's assume this is 3, 6, this is 6, 6, and let's assume this is actually 4, 12. So what I'm trying to do, I want to try this point to this point. So this will be the new location of A, this will be the new location of B, and this will be the new location of C, that is C prime. Now if I want to translate, what I first have to do, I have to find out what is the point of this one. So let's assume this one is 10 and 10 and 3. So we have 10 and 3 here. So as you can see, you can clearly say that, sir, this is 3, 6 and this is 10, 3. That means I have to add Tx will be 7 and Ty will be -3. So if I use Tx equals to 7 and Ty equals to -3, I can actually calculate the point, this one. Same goes for this one as well. Okay, if you use the same value of Tx and Ty, you will find this point, you'll find this point. And that's why this was actually important. So just by translating 3 points, we can actually get the full outline of the triangle. So that's why translation from one point to another point is important. Now let's go back to here. If I can actually translate a triangle, what I can do, I can also, same by following simple steps, I can translate the complex steps as well. Here, this is what they say, that we translate two-dimensional point by adding translation distances, dx and dy, to the original coordinate system xy. The point is affected by p, and the new point is, you see, is p prime, x prime, y prime, and the axis is you added is, let's assume, dx and dy. So basically new location of x prime will be x plus dx, y prime will be y plus dx. Just the way we did here, the new location of this point A will be ax plus tx, or you can say d, and then ay will be ty. So this was all about, we covered in the last class, and we have seen how vector work. And finally, we went to the example of triangle, scaling. So the theory of scaling is very simple. You have an object like this. What you want to do, you want to make the object larger or smaller. So we have seen that how and matrix work. So as you can see, if you want to zoom in or zoom out an image or a shape or an object, first what you have to do, you have to use a factoring effect called Sx in the x-axis and Sy in the y-axis. So Sx will be, so you see x prime will be Sx into x, y prime will be Sy into y. Just few ago in this one, in the translation, what we did, we actually added tx and ty. And in case of scaling, as you can clearly say, see, we will not add Sx or Sy, we will multiply with Sx and Sy. So this is the matrix. So we have Sx and Sy, and then we have 2 zeros in the corner. Why you have 2 0? I have said in the last class, this is associated with RC, row column, and so on. So Here, this is another example. So this is the first object, P. P has 3 points. What we are trying to do, we are trying to scale P. We are trying to change the size of the P. So there are two ways we can do it. We can choose the value of S that is greater than, we can select the value of S that is greater than 1, or we can select a value of S that is less than 1. So if the value is greater than 1, in that case, it will be a zoom. If the value of S is less than 1, it will be small. So we'll see some examples, don't worry. Just for now, let's see how it works. So we can write the components same way as we did in the translation. P prime x equals to Sx into Px. Previously in the P prime, what we read, Sx equal to, sorry, Px equal to Tx plus Px. And now we are using it for multiplication. Or in the matrix form, we can write S into P. Now, as I was saying, sorry. Yes. So if the factor is between 0 and 1, the points will be moved to closer to the origin. It will take less space. And if the size will be smaller, and here, this is an example, let the point P is 2 and 5. What I want to do, I want you to apply this Sx equals to 0.5 in this operation. Yes. Now, if the scale factors are larger than 1, the points will be moved away from the origin. The object will be larger. So in this case, you see, this is the example where the value of scaling factor is 0.5, 0.5. So this triangle actually became much more smaller. You can do the opposite. Next example, we have actually selected a large value that is greater than 1. And if you do the opposite as well, same way, the object will be larger. So let us see some examples here. See, when the value of Sx is 2 and Sy is 2, P prime actually becomes much, much more larger. So here is another example. So this is actually another here where the value of Sx is actually more than 1. Now there is one thing that is actually shown here. If you actually see, previously in the last example, the value of Sx and Sy was equal. The value of Sx and Sy was equal. But sometimes the value of Sx and Sy are not equal. So what happens in that case? Okay, so let's assume in this one, it's supposed to look something like this. If the yes, it's supposed to look something like this because we are using Sx equals to 2, Sy equals to 5. We're trying to zoom it out. Okay. And now, as the value here is 2 and 5, that means they're not equal, what will happen? You see this final shape of the object. You see the final shape of the object, the x-axis is in one shape, the y-axis is in another shape. If I say properly that the size of the x has increased only small and the size of the y increase have a lot. So basically, the point is that whenever the scaling factor is not equal, you will have a different shape. So if you want to make it like this, like instead of like this, if you want to make that the value of in the x-axis will be larger and the y-axis will be smaller, all you have to do in this one, the value of Sx will be 5 or 6 or 3, whichever, and the value of this one will be 5 as well. So sorry, my bad, 2 as 2 as well, because this is actually small and this is actually large. So we have to first decide how much we want to scale or how small we want to scale, and then we just have to apply this Sx and Sy, and this will actually give us a scaled result. Now let's go to another example. Okay, where is it? Here. So here there are 3 examples. Okay, I want everyone to practice it, then I will give the answer.